Okay, so now we come to the Russian quarter for the day. And it's my very great pleasure to introduce Slava Mukhanov, who's going to be telling us how predictive cosmological theories are.
Okay, thank you. At the beginning, I was thinking about giving some technical talk about singularities and let people sleep quietly. But then, okay, at a certain point, I started to think that perhaps right now something strange is going on in the literature and in newspapers. For instance, now not scientists tell to New York Times what is interesting, but New York Times tells to scientists what is interesting, as you know. Therefore, you have to convince some guy, okay, that he will write in New York Times. Then we have some kind of strange conferences, like one was in Munich, with the title, Why Do We Trust Theories? I couldn't imagine even that it can happen. No. Physicists started to discuss the question, what is the difference between a theory, the theory, framework, paradigm, and I think confused everything there. Now, there are 3 points of view could be, right, on the same thing. It could be optimistic, realistic, and pessimistic. Realistic sometimes is more close to optimistic and sometimes close to pessimistic. So I will be jumping between these two extremes. And let me start with the quote from Alan Guth. In fact, actually, I will not be making too much references because I don't want to insult anybody, yeah? And the only thing whom I allowed myself to refer to is myself, because I have the right to insult myself. Now, the quote actually I learned, and I was shocked by it even, okay, at some time ago, when Alan was giving public lectures, and he said, I think anybody who looks seriously in the history of science realizes that the old Popper's idea is not the way science happens. Rather, science is an arena of competing ideas, and right now inflation is by far the most widespread idea in cosmology. Now, I do not know about what kind of science he was speaking, because it could be also theology, but for physics, for sure, it's not true. Although I have sent actually this quote to some very respectable physicists, and I was even more shocked when he told me I agree with Alan. Then I suggested him that we can make proper taste of this idea. Gedanken, imaginable. Okay, if we would put Alan in the team together with Zeldovich and Sakharov, which was working on hydrogen bomb, for instance, then he could find out that it's not competition of the ideas. Because as you know, depending bomb would explode or not, these people would be executed or not executed. So, also, of course, it's not for the first time where these kind of questions are discussed in the nature. And when we go in the history, you know that, of course, everything was studied in ancient Greece. And there is a nice quote from the excellent, from my point of view, the best book on the history, written by Gibbon, where he noticed the physics both of the academy and the lyceum, as they are built, not on observations but on argument, have retarded the progress of real knowledge. You can tell me that Gibbon, of course, is not physicist, but I think you agree that Galileo was physicist. And as Galileo wrote, in questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. The modern observation deprives all former writers of any authority. Now, the title of my talk, How Predictable or How Predictive are Cosmological Theory, and let me give you my first experience with predictions from the most recent time. Of course, I could start with Friedman's and with Gamow, but let me go to Bicep, because when everybody was celebrating this discovery, I was crying, and for the simple reason, because if at this time you would take three statements. Theory is correct, Planck is correct, and Bicep is correct. Then you would find that they are in disagreement, because only this combination could work, but not theory plus Planck plus Bicep. Therefore, Planck plus Bicep, right, would be catastrophe for the theory. Based on this thing, I made prediction and even published it, but because I have no access to New York Times, I published it in Süddeutsche Zeitung, where people listen me. And, okay, here I wrote, or journalist wrote, who thinks he can explain the world by screwing the small n, as you know, spectral index, it gets to do with me, yeah? Perfect nonsense. The magazines are full of it, but still it remains nonsense. And then I predicted that, okay, what this guy see in Bicep, because I trust myself and I trust Planck team, either their own instrumental noise in Bicep or dust. If it happens that it was combination of both. What can I say? Now, but let me return back, because I recall this last survey where we had round table, around 1 kilometer size, when H. Kamatsu asked me a question. Okay, would you give up, because somebody also was complaining, what are the predictions now? 2014, there was no already prediction, because everything was confirmed, as you know, right? Then HR asked me, but if we will find the wrong spectrum for the gravitational wave, it will not be flat. Will inflation be dead or not? And because there was 1 kilometer distance, yeah, I could not understand his question, and therefore I gave, as usually politicians give, politically uncertain answer, or uncertain but politically correct answer. I told, find first. But then I started to think, could we get in inflation really non-flat spectra? And then, okay, let's go to the history. And what was the history in 80s? In the history, okay, there was quantum fluctuations, which is now unbeatable element of the theory, because according to Rubakov, who is one of the initiated, what I call alternative, in the theory of inflation, there is an element that has no real alternative. It's a mechanism for the generation of perturbation, strengthening the quantum fluctuation. Nobody offered, and all, any other mechanism and all alternative models use it. Now, then in 80s, there was only this line. So there was quantum fluctuations and 4 non-trivial predictions, so-called smoking gun prediction. Okay, at this time, people still understand inflation, okay, in the following sense, that it's inflation minus landscape and minus self-reproduction. Self-reproduction was already close, but landscape was far away, because at this time, string theory still didn't know that universe is expanding. Yeah, now, then, okay, when predictions were confirmed, of course, there appeared so-called alternatives. I will not specify it right now, but 2 perhaps most popular things is Rubakov, which is not so popular, but the most popular thing is so-called ekpyrotic cyclic universe, right? And even Paul Steinhardt doesn't claim that they made predictions. They made 4 postdictions. Now, the question is, can we spoil these predictions? And of course, the answer is yes. And after that, for 30 years, what we were doing, we were spoiling these predictions. And as I said, actually, I do not want to upset anybody, therefore I will give reference to my own phys report paper and chapter 3, which is called extensions, because half of this chapter is good chapter, and the rest I call garbage collections. So, and then in this paper, we investigated all kinds of possibilities. How can you spoil good normal inflation? First of all, you can imagine, of course, everything with fine-tuning, double inflationary models. Then, in double inflationary models, when Hubble constant was jumping like this one, we managed to discover this spectra for the gravitational waves. Okay, so because you understand that gravitational wave spectra, according to H, will be measured, and according to Irania, within a certain range of the interval, okay, which is not so large, by the way, it's either a small multiple or a multiple between 80 and 100, you can move this part and then you can get any spectra as you want, you see? Now, also we notice that this effect can be applied for both adiabatic and entropy perturbation, because in the models with two scalar fields, there was no problem to generate any kind of spectra, any kind of any kind of features in the spectrum, and we could actually also get all kind of possible non-Gaussianities. But just you take, for instance, Newton law before it's checked, and start to add, leave it for 1,000 years with the 1,000 series, okay, without experiment, and can you imagine what they can do with it? Here was more or less the same story, but nevertheless, after that also I wrote some papers, so don't think that, okay, I was not writing paper about all these things. You have to check and test these things, of course. How easy to spoil. But nevertheless, it was already clear in 92 when there was no experiment. And we wrote it clearly in physics reports that, however, such a procedure is extremely unappealing since it applies complete loss of predictability. At this point, I mean, when I was younger, I was a little bit softer. Therefore, now I would formulate the same sentence that for me, inflation is the theory only when it's understood as the stage of unbroken accelerated expansion due to the same ingredient which is responsible for quantum fluctuation. Otherwise, it's rubbish without any predictions. Now, okay, in this case, if we will accept this definition, inflation becomes completely unbeatable as predictive theory because it allows us to calculate the effect of amplification of quantum fluctuations in completely controllable weak coupling regime, as actually Ed Wheaton noticed when he was comparing inflation with alternative. While most alternative cannot even compete with rubbish inflation in a sense of controllable reproduction of outcome for quantum fluctuations. Neil is here or he still didn't arrive? Neil Turek. Because I would be happy to hear his criticism. So now, therefore, what I suggest to do, I suggest to accept this formula. Let's take cosmology, extract from it theology, and assume that inflation was expanding exponentially during at least 70 folds, but less than 1 million folds. You will understand why less than 1 million folds. Because in this case, no any problem with predictions, which could falsify the theory in proper sense. Now, what is relevant for predictions? In fact, not so much. Namely, effective description of the stage of accelerated expansion in terms of the energy density and in terms of pressure. And namely, we have to assume that the equation of state satisfies this kind of condition during at least 70 e-folds. 70 e-folds, e-fold is defined like this one. So scale factor is equal scale factor at the end of inflation multiplied by exponent minus n. N is called e-folds. So, therefore, the only thing which we have to know for the predictions is that 1 plus w was much smaller than 1, for n larger than 1, was of the order of unity when n was 1, the end of inflation, so it means smooth, graceful exit, and we will assume also that 1 plus w is a smooth function of the number of e-folds. I know that some people like, for instance, functions which takes value 1 in rational numbers, some people, and okay, 0 at irrational numbers, but I'm not going to deal with this kind of situation. Now, okay, from this effective description, let's go to so-called models, because I have read in some place that inflation is not a unique theory, but rather a class of models based on similar principles. From my point of view, it's wrong, just flatly wrong, because the only purpose of inflationary models relevant for observation is the mapping of some kind of scalar field potential or curvature term to this equation of state. And this mapping happens to be not so crucial for robust predictions, but important only for excluding definite potentials, which anyway we will never be able to verify in any other independent experiment. Now, from all these potentials, what is relevant for observations is, in fact, okay, the behavior first, one point in the potential, and then some combination of its first and second derivative. Therefore, when people write potentials like this one, or draw potential like this one, and everything what we need from these functions, one point and a couple of derivatives, honestly speaking, I cannot understand. Yeah? Maybe somebody else can understand, but of course, on the top of this potential comes a lot of what people call fundamental theory, which in fact we do not know anything about it, because as I said, fundamental theory is not the question who likes whom and who likes what, because for some people something can be beautiful, while for the others the same thing could look ugly. Therefore, this question, theory is beautiful or ugly, we are not going to discuss. So, now, okay, as I said, for prediction, the only thing is relevant change of the equation of state, as I said. And the only reasonable function which I can draw are like this one. And the only range which is relevant for observation among all this kind of function is the range which corresponds to the number of e-folds around 50. So you see, it's not too much. Therefore, the only thing you have to assume that you don't have this kind of nonsense here in between. So it should be smooth. Now, all these functions, okay, could be well parameterized by some number of the order of unity, which is, by the way, becomes not so relevant, divided by the number of e-folds till the end of the inflation in some power, where this power is a free parameter. If you want, you can write here logarithm n in any power, and then if you will take Encyclopedia of Inflationary Scenarios, which was published by French, okay, with, I think, 300 scenarios, because they didn't include all of them, that all these scenarios could be mapped just to two numbers, alpha and beta, and some gamma, which is irrelevant. After you did this assumption, you immediately come to four robust predictions, which were there in 1980, and in 1980 they were contradicting to all the observations. People who were not living at this time, they have no idea up to what extent, okay, this theory was looking ridiculous from the point of view of experimentalists. If you would tell experimentalist or observationalist that the universe is flat, then he would immediately give you advice to go and visit your psychiatrist, because psychologists would not help in this case. So, perturbations are adiabatic. Nobody in the whole world was doing adiabatic perturbation besides of crazy Russian in the Zeldovich group, because they were in all kind of possible contradiction with all observations. Of course, at this point, the most popular thing was theory which was suggested in Princeton by Jim Peebles, entropy perturbations. But you know that Princeton is not always right, or maybe always non-right. I don't know how to formulate it more politically correct. Now, small non-Gaussianity. It means that, okay, perturbation should be Gaussian. In 80, there appeared the theory of cosmic string. In 89, there appeared the theory of cosmic textures. And I recall, 93, Neil Turek going to all the conferences and telling, look at these pictures. It's clearly cosmic textures. You perhaps remember this thing, if you remember. And the red tilted spectra, namely there was prediction for the spectral index. Now, you see, again, in some texts it's written that inflation predicts that ripple should be nearly scale invariant. What I say, it's wrong in inflation, how I understand it. It never predicts scale invariant or plus minus something. It always predicts red tilted spectra, and this is my transparency from Cambridge workshop in 2000, where I wrote the spectrum is never Harrison-Zeldovich, and this is generic prediction of inflation. Or for instance, in 2003, in one of the paper I wrote, contrary to an erroneous belief, inflation doesn't predict the scale invariant Harrison-Zeldovich spectrum, the spectral index should be always in this range. Now, from where it follows? In fact, actually, it follows from need to finish inflation, and it follows from the fact that there should be red-tilted logarithmic spectrum, which I found with Chibisov and Steven found independently around 81, 82. And according to this kind of prediction, spectral index should be equal 1 minus some number, which depends on the particular model, but irrespective of the model, it's always, in my parameterization, if I use this kind of class, larger than 1.5, and there is parameter b here, which should be between 1 and 100, depending how much effort we have since the end of the inflation, okay, before the end of the inflation, which is responsible for large-scale structure. And people are using an experiment numbers between 50 and 55. And in fact, to know this number exactly, we have to know exact theory of reheating and particle physics, which we will never ever know, because nobody will give money to build accelerators to this energy, and if they would give even money, we would not build accelerators because this energy is 1013 GeV. So spectrum prediction is smaller, spectral index smaller than 0.97. And I recall that Andrei was comparing this thing with prediction of logarithmic running of coupling constant in QCD, because finally actually it led to these things. Now, of course, in 2003 there was not yet dream to see these things, therefore Lyman Page at a certain point wrote to me specifically, if NS 0.91, would you throw in the toil on inflation? I wrote to him, if you will find that it's 0.99 plus minus 0.01, 3 sigma, I would throw in the toil on inflation. No problem, you see. Now, what we know right now, we know that, first of all, okay, all these predictions were confirmed. They were really predictions. The other thing, the arbitrariness of the parameter b, which we will never be able to fix, means also bad news for model builders, because it leads to theoretical uncertainty in prediction of spectral index of the order of arrow bar, which at current state we reached on accelerators. And therefore, improving accuracy there, I don't know how to do it, but perhaps it's impossible even, will not help us too much because we do not know the theory, you see, and we will never know the theory in so big details to fix this problem. So, and further increasing of experimental accuracy in S will not help us too much in model selection. And also, you know, by the way, also for each R and N, there are at least 3 models, okay, which would satisfy all criteria within given, how it's called, reasonable experimental accuracy. After that, how you will select out of these 3 things is again big question. Now, inflation, of course, has further prediction, which I was always considered as non-smoking guns. First of all, primordial gravitational wave and non-Gaussianities due to unavoidable non-linearities of Einstein equation. You can calculate using just Einstein equation 3, 4, 5, 6 point correlation function. At a certain point, you stop, perhaps, and then could ask me to compare this thing with observations, but we have to keep in mind that we have to be realistic concerning observation. Now, what about gravity wave? we know that the ratio scalar, tether to scalar ratio is given by this formula, and it's again determined by this ratio of the number of the order of 1 by n alpha. Alpha could be 1, 2, 3. For instance, for new inflation, it's 3. For so-called Starobinsky model, it's 2. For all models, okay, with power low potential, it's 1. Therefore, you see that you can change the amount of gravity wave by factor 50 very easily. But now, after we measured spectral index, situation changed in the following sense. You see, here is the amplitude of the scalar perturbation. We fix spectral index 0.96. This point is fixed by observation as a point of normalization. And then you are arriving to the energy scale at the end of the inflation, which is about 12 orders of magnitude below than the Planckian scale. And then you understand that the amount of gravity wave cannot be lower than this thing. Otherwise, you have to assume that your Hubble constant was not dropping or constant, but it was growing during inflation. And this is optimistic prediction, 0.2 for m squared phi squared theory. Now, therefore, of course, the purpose of experimentalists should be to go to this number. But if we will not find gravity wave at this level, does it mean any trouble for inflation or not? Let me show you that at the level of 2 sigma doesn't mean any trouble. Why? Because within 2 sigma level, due theoretical and experimental uncertainty, spectral index could be 0.95. But in this case, a low limit would become 7 times smaller. That's what I gave. You see, and it's perhaps, I do not know, but H0 can tell me, not very realistic for next perhaps 50 years. Maybe in 150 years it will become more realistic, but for next 50 years impossible yet. Thus, detection of the primordial gravitational field will provide us an extra confirmation that quantum fluctuations were amplified on the stage of accelerated expansion. Failing to detect them at the level of 0.04 would not have any implication and in no way can be considered as a proof of alternative for amplification of quantum fluctuations. Now, concerning non-Gaussianity, situation is even worse from the point of view of experimental physics. Because, of course, people calculated that from inflation you have this thing. But one should never forget that from subsequent perturbation evolution, because of non-linearity of Einstein equation, you will get 2 and 4. And you know, right now, because of cosmic variance from CMB, we cannot get anything. Therefore, we have to go with 21 centimeter, or actually with this non-linear structure, but then I do not know how to deselect the whole thing. So what are the perspective of measuring F? But from my realistic point of view, here it's rather pessimistic, okay? I don't think that it's extremely promising, at least for next 20 years. Now I have 1 minute, or 5. 5, it's more than enough, because now I finished with physics and I go to theology. Okay, and let's ask question. Multiverse or one universe? I think from the point of view of physics, both statements are equally correct or wrong, because you can never falsify and you can never verify them. But why this question arises at all, and why it produced so much noise in Scientific America and in New York Times mostly? Okay, because, of course, it's related with the question about initial condition for perturbations and for the universe as a whole. There is no problem whatsoever with initial condition for perturbation. One can begin with arbitrary inhomogeneities, provided that they do not destroy right away the stage of accelerated expansion. As a result, all garbage which was there will be thrown away from the observable part of the universe, and remaining quantum fluctuations will be amplified and produce galaxies. Comparing to alternative, for instance, cyclic universe, this is opposite situation. In the case of inflation, okay, perturbations, garbage is thrown away from the horizon. In the case of alternative, horizon is collector of garbage. Therefore, in alternative, you should be very careful with fixing initial condition. When people say, not Harrison Zildovich, Bunch, Davis, Vacuum, etc., up to now I cannot even understand what do they mean. Start with arbitrary initial condition, just claim you have, after that, inflation, and everything is solved. In the case of universe, there is actually some problem, because if you will be not reasonable, yeah? How generic are initial conditions for the universe? Are there any problem with them in inflationary cosmology? You say that before inflationary cosmology, everybody was thinking how difficult to produce universe. When inflationary cosmology appeared, people started to see how easy to produce universe. You see, change of the attitude. And in fact, this problem with easy production of the universe, I discovered, was noticed in the paper by Braut, Englert, and Gunzig, 79, who used also to produce from Minkowski space universes using P minus epsilon, where they wrote, we must not make too many universes. What do they mean? I have no idea. Okay, would be they satisfied with 100 or 1,000? But I think here there was no yet problem. Why? Because if this infinite number of universes even would be produced, but all of them would be the same concerning statistical properties, it would not damage theory anyway. We would just predict, okay, that we live in typical universe and what are the typical universe properties. But the other problem, which was noticed by Andrei, actually came later. It was namely the problem of self-reproduction, which finally merged with landscape, managed to lead to the statement like everything what could happen is happening. Then I know, because I also was participating in this case, that there is not so easy to find natural choice of natural measure, and even Boltzmann brains can appear there, as you have read. You see, what can I say? I think it's a good discussion for after-drink conversation, yeah, but not for scientific talk. After W and Planck, but here there was not yet problem to start with Planckian energies. And then at Planckian energies, of course, you have no parameters, so you can forget about fine-tuning. But when Planck happened to give potential of this type, then, okay, Steinhardt, Loeb, and Anna, yeah, okay, one more minute, after this minute, and we are finished. So, after these things, they wrote paper in 2013, Planck produced trouble for inflation. Why? Because if potential is like this one, you have the number 10 minus 12 here, then to produce inflationary universe, you have to jump from Planck scale down, and you have to produce region which is few orders of magnitude larger than the Planckian region. And when you have in your hand 10 minus 12, then you can write exponent in power 10 minus 10, 12, okay? Or you can produce as a nonceless number, because when people speak about probabilities, it's not even clear what these probabilities means and how, okay, they are defined. Now, therefore, 2 years ago, I raised the question, because you can kill very easily self-reproduction. You just can jump here from down, okay? And then start from here your inflation. But then there is fine-tuning problem. You can solve fine-tuning problem raising potential like this one, like m squared, phi squared, but then you will have self-reproduction. I ask question, can we nevertheless avoid these two problems simultaneously? And okay, I found that yes, we can simultaneously avoid self-reproduction, and it's unpredictable multiverse, multi-mess I wrote, it was a quote from Steinhardt, and fine-tuning. What you do, you just take unique class of potentials like this one, okay? And then you start inflation here, naturally go down, okay? Inflation continues. When you start with the Planckian densities, all numbers are of the order of 1, and you can stay on your ears, but you cannot make small numbers, therefore no fine-tuning. And if there is no self-reproduction, you are getting just collection of similar universes, and I can make even in this theory predictions that in billions of billions of billions, okay, let me stop at this moment, yes, you should see very large of the order of unity quadrupole component for the radiation. So it's also predictive, but okay, not realistically predictive models. Therefore, okay, as you understand, from my point of view, there was never any trouble, and I do not understand what all this talks about. And I think concerning, instead of conclusions you can make yourself. Let me finish at 0 minutes. Talk is finished. Talk is finished, yeah, I understand. Let me tell you my opinion, yeah, about origin of the universe as whole. And in this case, I think that only thing which we know is nicely described in Talmud. And I got this story from Francois Englert. You see, when God was borrowed to be alone, he decided to make something nice, to produce universe, but then God was in trouble. And then he thought a little bit, shrinked himself. In remaining space, he produced universe, expanded, and found himself in extremely boring universe because it was too symmetric. But in Talmud is not specified. It was Minkowski, de Sitter, or anti-de Sitter. This I don't know. So then God thought a little bit more, shrink himself again to the point. But before shrinking, he distributed a little bit garbage around. And then when he expanded, he found himself in nice expanding universe. And this idea in Talmud is expressed only by breaking the divine configuration can be perfected. And I think today we know what kind of garbage he spread it around. He invented quantum mechanics. Okay, thank you very much.
So if I can just remind people when they ask a question to wait for the microphone to come, and we'll start with Jim.
Do you think it's an important question for inflation to see it as embedded in current theories of elementary particle physics, which would specify the potentials possibly, and in theories of the initial condition, like
yes.
Stephen's wave function of the universe?
Yeah, I think it's extremely important. The only problem that I think that we have no slightest idea about series of particle physics beyond the scales which were reached on LHC, as you understand. Now, the question, which you ask second, concerning actually these ideas about quantum production of the whole universe, I consider as extremely important because it's mathematical description of blah, blah, blah when we give some kind of argument why universe should appear so easy. There should be some kind of quantitative measure, you see? And I think in this case, your work goes in this right direction. Yes.
Many of these multi-mess related discussions seems to arise on the point that you cannot actually define what is fine-tuning, irrespective of the person who's defining it having some subjective beliefs about it. What is your definition of fine-tuning?
I don't have this definition of fine-tuning. I just use this word from the other people because, as I said, I have no idea what is probability there. Of course, I am not as rigorous as my friend Alan Kohn, who still lives in Euclidean time, because he's a mathematician. But nevertheless, I also have some kind of little test. What does it mean, for instance, probability? And it should be within reasonable criteria of rigorousy. When people say fine-tuning, for instance, for the huge universe, then there was number 1090 causally divided regions. Of course, even in this case, you could not define what is the measure. But everybody knew that, it looks a little bit ridiculous and unnatural. And after that, you come and make everything from one causally connected region. Then some people are unhappy. Oh, we have self-reproduction, we have God knows what. I love to live cyclic universe, with infinite number of cycles. I don't know why they love to have infinite number of cycles and why it's better from philosophical point of view than production of the universes like this one. If they are all the same, I do not see any problem, you see? The problem appears when you start to merge the things, and then after that, okay, for instance, to explain cosmological constant, you give completely predictability of the things which are there. Then you can restore it partially using anthropic principle. But you understand that anthropic principle is the other disease which I don't want to discuss.
Almost seems like a good way to
Yes.